In this video I'm going to be going through visible light and the solar system, which can be used for some revision for your upcoming assessment point for year 10 physics. So the double science students, this is applicable for you guys as well. So I want to go through each of the bits one by one. I'm going to start on visible light and the solar system, so all of this video will be based around that. Okay, so I'll go through the assessment first and I'll highlight some other key points in the revision document. So it says over here, to get a grade E, you need to know the 8 planets in order of distance from the Sun, state the difference between a geocentric and a heliocentric view of the solar system. Okay, so remember, when you've got the 8 planets, okay, you start from the closest, you go furthest out. That's what it's asking us to do in terms of distance from the Sun. So there's a way of remembering it, and that's my very easy method, just speeds up naming planets. That's 9 planets. Okay, so remember, Pluto is no longer a planet, the P planets, so that's no longer a planet. So instead it's Mercury, Venus, Earth, Mars, Jupiter, Saturn, speeds up, so that's Uranus, and then Neptune. Alright, so that's the order of the planets. In terms of geocentric versus heliocentric, if we look at our notes, okay, so if I just scroll down over here, okay, you can just see, I've just flipped past it. There we go. Okay, so we've got some notes here on a geocentric and a heliocentric view of the solar system. So there's heliocentric, okay, there's geocentric. So in terms of geocentric view, it's where everything goes around the Earth. For geocentric, everything goes around the Earth. The Moon and all the planets go around the Earth. In a heliocentric view, everything goes around the Sun. So all of the planets go around the Sun, apart from the Moon, which we believe goes around the Earth. Alright, so if we go back to the very top, look at our second one. It's saying to draw a transverse wave and label the following features: amplitude, wavelength, and frequency. Then it's asking us to also write out the wave equation. So if we go to that section of our work, okay, here we go. So you can see there's a transverse wave over here, okay. There's the wave equation. This top one over here is the wave equation. Right, so the amplitude, remember, you should have a definition of that, is the height of the wave. The wavelength is the length of one wave in meters, and the frequency is the number of waves per second. It should really be passing a point in hertz. So it should really put passing a point in there as well. Amplitude and wavelength you can actually label on the diagram. Frequency you cannot, but remember, frequency is the number of waves passing a point per second in hertz. Right, let's scroll back up. If you want an example calculation on wave speed, okay, there's an example calculation just below over here. Okay, so you can see up to there. There's an example calculation on wave speed. Right, compare and contrast transverse and longitudinal waves and give examples of both types of waves. Okay, so you need to know about the similarities and differences when you're comparing and contrasting the similarities and differences between transverse and longitudinal waves, and you need to be able to give examples of each. So here we go, got a transverse wave. The particle motion, that's key that you say it like that. The particle motion is at right angles to the direction of the energy of the wave. The particle motion is at right angles to the direction of the energy of the wave. You can see for a longitudinal wave, the direction of energy travel is parallel. It's in the same direction of energy travel for the wave. So in this one it's perpendicular, and this one it's parallel. That's how you compare and contrast the two. In terms of examples, well, you've got a whole bunch of examples here. Examples of transverse waves, so you've got electromagnetic, S waves, waves on a string and spring, and ripples on water. Okay, and for longitudinal, mainly sound waves are the one we talk about for longitudinal, so that's infrasound and ultrasound as well, but also some seismic waves such as P waves and waves on a spring that you push or pull. Alright, so that's all the bits we need to know for grade C. So it's transverse and longitudinal, compare and contrast, and examples. Right, so to describe with the aid of the diagram how to find the focal length of a converging lens. So this is one of the experiments that you would have done in class. You guys would have done it in year 9, so it's been a bit of time since you've done it. So what I've done is I've actually labelled it in a very clear way over here. So you've got a little picture of the experiment, but you've also got a few notes about it too. So the first thing is you need to set up an object, okay, the lens, okay, and a screen. Okay. It's best if you're using a faraway object. It works really, really well. So say a tree from a window, if you're trying to get that works really, really well. You clamp all of these in place. The reason why you clamp them in place is so that you don't want them sort of moving around. So if they're clamped in place, you can make very clear measurements. You then want to move the lens until, you're going to keep moving it backwards and forwards until you get the image sharp in focus. So when I mean in focus, I don't mean blurry, but with very clear lines. As soon as you've got that, you clamp everything in place. So you can even move the screen or the lens, whichever, to get it sharp in focus. As soon as you've got that, you put everything in place and you measure the distance between the lens and the screen. That is the focal length between the lens and the screen. The focal length is the distance between the lens and the screen. Okay? So in other words, it's this distance here between that and that. Okay, so that's your distance, that's your focal length there. The only other thing I want to point out about this is that if you repeat this experiment a few times, that's good for reliability. So don't just do it once, do it a few times over to improve the reliability of the experiment. Okay, so we've done that one. Okay, so that's cool, we've done that, the focal length of the lens, we've done that. Explain how reflecting and refracting telescopes can be used to magnify an image. Okay, so we need to go to our section on telescopes. Okay, so it's just beyond this. Okay, so with a refracting telescope, they've got an objective lens and an eyepiece lens. Okay, so what it's doing is it's taking in light, it's refracting it, and then the eyepiece lens magnifies it, so it makes it bigger so that it feels more of your eye. Okay, so objective lens collects the light, takes it in, and the eyepiece lens magnifies it, makes it bigger so it feels more of your eye. Reflecting telescopes do the same, but they use mirrors rather than lenses. Okay. So you can see that they use mirrors over here that reflect the light back, get out through the eyepiece to the eye. Once again, there's an eyepiece lens which magnifies the image to fill your eye, okay, but they use mirrors to get a much clearer image. Okay, reflecting telescopes, remember, use mirrors. Okay, the angle of incidence equals the angle of reflection to get a much clearer image. Refracting telescopes sometimes have chromatic aberration. Okay, sometimes the lenses aren't perfect. Okay, that means that you don't get a particularly clear image all the time from a refracting telescope. Refractors are cheaper though than reflectors. Okay, so we talked about how they make an image. That's great. So they're both magnifying image. The last one is explain how Galileo's observations helped to prove the heliocentric view of the solar system. Okay, so what we've got to get our head around is the fact that what Galileo saw, skip past that, what Galileo saw was 4 moons of Jupiter. That proved that geocentric was wrong, but it did not prove that heliocentric was right. It proved that geocentric was wrong because you didn't have 4 moons. If there's 4 moons of Jupiter, everything did not go around the Earth. Some things went around Jupiter. It didn't prove that the heliocentric was right because it didn't show that all the other planets went around the Sun. Okay, so that's why Galileo's observations didn't prove the heliocentric right. It did prove the geocentric right, wrong, but did not prove the heliocentric right. Okay, so most people started to believe the heliocentric because the geocentric got proved wrong. So that's everything for the assessment over there. The only thing that I want to tie in over here that could crop up on your census point is things about the universe. Okay, we actually have new technology that allows us to observe the universe in different ways now. Okay, so main things is things like photography. Remember, the benefit of photography is that you can come back to the image and study it time and time again. Also, you can use photography to take an image over a long period of time rather than just a snapshot you get from a telescope. Okay. And remember, we use different waves nowadays to investigate the universe, not just light. We can use X-rays and gamma rays, but you learn more about that when you do about the electromagnetic spectrum. There are 2 types of images you need to know about. Okay, they're called real and virtual, or real and imaginary, sometimes people call them, but real and virtual are the phrases you should be using. Real images can be projected, virtual images cannot. Okay, refraction, remember you need to know about. The key thing you need to know about refraction is that it's when light changes direction due to a change in speed, due to a change in density. Okay? When light changes direction due to a change in speed, due to a change in density. Okay? And that's it. There's an example calculation that you have here in your notes. I'd certainly go through that to make sure you understand how that example is actually calculated. Okay? Thank you very much for listening, guys.